येते आता बघा. येत नाही, येत नाहीये. Okay. Good morning, one and all. Myself, Dr. Prashant Pingai, Vice Principal of Gokhale Education Societies, Sir Dr. M.S. Gosavi College of Pharmaceutical Education and Research. It feels a great pleasure to talk on fourth webinar. In fact, it's a one-day national webinar on exploring pharmaceutical innovations, the future of pharmacy, organized by Department of Pharmaceutical Chemistry under the aegis of IQAC of our college. Gokhale Education Society was established on 19th February 1918 by Principal T.A. Kulkarni, who was a great social worker on the occasion of third death anniversary of Namdar Gopal Krishna Gokhale, who was a spiritual guru of Mahatma Gandhi. Recently, our society completed 106 years of meaningful existence, and today, about 140 units are spread over 3 zones of Mumbai, Nashik, and Thane. We have about 1.25 lakh students. Previously, Gokhale Education Society was led by late Principal S.B. Pandit, who was the president and great visionary and eminent personality. Late Sir Dr. M.S. Gosavi, Secretary and Director General, who rendered invaluable service of 65 years in the field of education. At present, our Gokhale Education Society is led by Dr. Mrs. D.P. Deshpande, Secretary, playing a crucial role in overall progression of Gokhale Education Society. Our college, Gokhale Education Society, Sir Dr. M.S. Gosavi College of Pharmaceutical Education and Research, started in 2012. Presently, we are offering PhD in Pharmaceutical Sciences, M.Pharm in Pharmaceutics and Pharmaceutical Quality Assurance with intake of 15 seats each. B.Pharm program, which is permanently affiliated to Savitribai Phule Pune University, Pune, with intake capacity of 100 seats. And D.Pharm program affiliated to MSBTA with intake capacity of 60 seats. Last year, in October 23, we accredited by NAC for 5 years with A grade with 3.22 CGPA out of 4 scale. Before that, we got accredited by National Board of Accreditation from 2019 to 2022. The college has state-of-the-art infrastructure and has a lush green surrounding, which provides favorable surrounding for students to grow not only as a good pharmacist but as a world-class citizens. College has experienced and qualified faculty members with academic excellence. College maintains a tradition of good academic results and organizes various activities including conferences, seminars, workshops, student and faculty development programs for overall development of student and faculty to bridge the gap of academia and industry. Today, we have a webinar on exploring pharmaceutical innovations, the future of pharmacy. Basically, the idea of webinar is to collect an information throughout the globe. Today, we have about 1875 plus registrations to this webinar. This is the fourth webinar series of this academic year. We started webinars since July 2024 for this academic year. We have 3 speakers today. Dr. Yatin Gadkari, Assistant Professor at ICT Bhuvaneshwar. Second speaker is Dr. Ruksana Pinjari Madam, who is Principal at Siahgad Institute of Pharmaceutical Sciences, Pune. And third eminent speaker is Ms. Priyankita Hire, who is working as Database Coordinator at LabCorp Drug Development, who is our ex-student. 3 speakers. The idea behind putting all these three speakers is that one is eminent academician or industrial expert, the second speaker is our alumni, and the third speaker is ex-student of coordinator. The intention behind keeping all these three speakers is to elevate an interaction between our alumni and our existing students. However, ex-student of coordinator, the idea behind this is we are not only associated with our student, but we are in contact with our ex-students also. So we have first session today. We have Dr. Yatin Gadkari sir. Now I request Miss Harshal Chavan madam for introduction of Dr. Yatin Gadkari sir. Madam, please, over to you.
Start करो. A very good morning to one and all. I, Mrs. Harshal Chavan, working as an assistant professor on behalf of Gokhale Education Societies, Sir Dr. M.S. Gosavi College of Pharmaceutical Education and Research, Nashik, welcome you all to one-day national level webinar on exploring pharmaceutical innovations, the future of pharmacy, under the aegis of Internal Quality Assurance Cell, organized by Department of Pharmaceutical Chemistry. It is It is my honor to introduce esteemed speaker for today, Dr. Yatin Gadkari sir, who is going to deliver his session on green chemistry, a path to eco-friendly API processes development. Sir is currently working as an assistant professor at Institute of Chemical Technology, Mumbai, Indian Oil Campus, Bhuvaneshwar since August 2022. Sir has previously worked as an assistant professor at ICT Mumbai Merge Campus from January 2022 to August 2022. Sir has also worked as a lecturer at Niharika College, Nagpur. Sir has been a research fellow at Principal K.M. Kundanani College of Pharmacy, Mumbai. Sir was a research trainee at Unicum Laboratories. Speaking about his educational qualification, Sir has pursued his PhD in Pharmaceutical Chemistry Department from ICT Mumbai, M.Pharm in Pharmaceutical Chemistry from K.M. Kundanani College of Pharmacy, Mumbai with first class, and B.Pharm in Pharmaceutical Sciences and Technology, College of Pharmacy, Nashik with first class. Sir is currently guiding 13 MTech and 1 PhD student at ICT. Sir secured first rank in the Institute of Chemical Technology PhD entrance test in 2018. Sir has been invited as a speaker at Green Energy and Sustainable Environment Technology GESCT 2022 by Kalinga Institute Industrial Technology. Sir has successfully qualified various entrance exams like GPAT in 2010 with All India ranks 479, ICT entrance, BITS entrance, NIPER JEE in 2010, and also GATE in 2009. Uh, Sir has been selected for the prestigious 2024 Internal Young Scientist Research Project by Korean Scientific Society, Ginseng. Sir is having 6 international research papers as the first author, 8 international research papers as a co-author, and 7 international research papers under the progress as a corresponding author. We are glad to have you, sir. Without further delay, I request Dr. Yatin Gadkari, sir, to proceed for his session. Please, sir.
Thank you each and everyone. And I would like to thank the principal, vice principal, sir, coordinator, and I think principal sir is Amrutkar sir, and Pindir sir as vice principal, and Dr. Shilpa Harak madam for inviting me for this talk. And the topic is also the theme of this webinar is also such a made for the future of B Farm, M Farm students as well as MTech students. So hope this webinar will help all the students to look into the research aspect of pharma, and they can this webinar will actually guide them to choose their relevant field for the research for the future. So I really thank, and I'm very much humbled in speaking in front of all seniors, actually, as I'm very much junior to all of you. So thank you. So I'll start as it's a 10:40 and I have to cover the topic within 1 hour. So I'll start with the topic: the green chemistry, a path to eco-efficient API process development. So as we see the title, actually, so the title, just by looking at the title, we'll get an idea that the topic is related to API process development. What is the API? API is an active pharmaceutical ingredient, or its intermediate, we can say. And definition of API as per WHO, all of you know that it's an any substance or combination of a substance used in finished pharmaceutical product intended to furnish actually any pharmacological effect or to otherwise direct have a effect in diagnosis, cure, medication, treatment, cure of a disease actually, and also restoring our body physiological functions, correcting, modifying physiological functions in our body. So API is not a narrow term. It's a actually we can say broad term actually. So as all of us actually consume a API in the form of tablet, capsule, parenterals, injectables on a regular basis. Whenever we get COVID, whenever we get cold, we take some cetirizine or CPM tablet actually. So API is a need of our actually life. So synthesis of API is a crucial aspect. First thing, and second thing, API and its intermediates are synthesized by various companies in India actually. So we are going to discuss in the API process development as well as API intermediate process development. So as the title says, green chemistry, a path to eco-efficient API process development, it means that we have to develop a process for synthesis of API using green chemistry principles that should be economical as well as eco-friendly. So we will just go through the contents. First, we will discuss about concept. Next, we will discuss about process development. Then we will discuss about hazards associated with chemicals. Then we will discuss about some green chemistry principles. And then we will discuss about the research case studies and the case studies which I actually worked on, that also I have included. So we'll think of now concept initially. So I have taken this example of synthesis of sulfanilamide. The purpose of taking this example, because many of the students are in a third year, or many of the students have completed third year, final year, some have just started intake. They are well versed with this sulfanilamide synthesis actually. So if you see the sulfanilamide synthesis, we carry out a practical around 3 to 4 weeks. We carry out this practical starting from nitrobenzene or aniline actually. So if we see the sulfanilamide synthesis starting from benzene, you get a nitrobenzene using nitrating agent, which is a nitric acid in presence of H2SO4, which act as a acid catalyst. Then from nitrobenzene we get a aniline using tin and hydrochloride. Then we get an acetanilide by using acetanhydride. Then after acetanilide, using chlorosulfonic acid, we get a 4-acetamidobenzene sulfonic chloride. Then using ammonia solution, which act as a base, we get a 4-acetamidobenzene sulfonamide. And finally, then by hydrolysis, we get an sulfanilamide. So if you see this synthetic process, actually, if you get this sulfanilamide, if you will see that multi steps are involved. Just like sulfanilamide, this multi steps are involved. Similarly, for other APIs or API intermediate synthesis, similar kind of multi steps are involved. So what is a process development? Is that whatever the traditional methods are there, like using of H2SO4, HCl, which are harsh chemicals actually. The handling, storing of that is not that much easy. So what is meant by process development? That replacing the harsh chemicals with greener chemicals. So that is a green chemistry. And the whatever the method we will develop using green chemistry is a green chemistry assisted process development. So our topic is green chemistry eco-efficient process for process development. So use of green chemistry actually. So in this actually sulfanilamide actually synthesis, you will go through sci-finder reaxis. You will find out actually various routes are there for synthesis of sulfanilamide. Here you can see around 4 to 5 steps are given, but some researchers have developed a methodology for sulfanilamide synthesis within 3 steps as well. Somebody has used some greener approach actually. So that is a method development or process development. The eco factor is very important, which signifies the eco-friendliness as well as it should be economical one as well. So we will start with what is a process development. So chemical process development is a set of research, design and engineering activities accompanied by economic studies, which transforms a recipe for carrying out a synthesis in laboratory into industrial process that is environmentally friendly, fulfilling safety and good manufacturing regulations, and it should be profitable. In sum, it should be best process. Means what? What is a chemical process development? It is a set of a research, design and engineering activities. So the pharma field is a interdisciplinary research. Whenever we synthesize any product, we synthesize any, just like in previous slide we have discussed about sulfanilamide synthesis actually. So sulfanilamide synthesis we are carrying out on some gram level actually, but when we have to carry out the synthesis on a tons level, that is a scale up, that is called as a scale up. If you want to scale up it to higher version, we need engineers to design a reactor. So all this should be accompanied by economical studies. It should be economical, it should be profitable for industry, and we have to transform that laboratory study into industrial process, and in such a way that it should be environmentally friendly, it should fulfill the safety aspect as well as good manufacturing practice. So in essence, we can say the original recipe is usually modified during process development. The selection of most advantageous method of product isolation and purification and effluent treatment, the most suitable sequence of operations, the best full-scale equipment are the essence of process development. So what is the essence of process development? The selection of most advantageous method of product isolation. Many times what happens that when we synthesize a product in RBF or in a reactor, getting a final product actually in a pure form, in a spectroscopically pure form is very tedious process because of formation of impurities, side products, as well as the remaining of some reactant. So the product isolation is very important. All of you know that there are different types of catalysis: homogeneous catalysis, heterogeneous catalysis. So what is a homogeneous catalysis? Homogeneous catalysis is what? Where all the reactant catalyst are in one phase. That is an homogeneous catalysis. So what happened in the homogeneous catalysis? Actually, the reactant catalyst are in same phase. They are in one phase. Because of that, chemical reaction happens very smoothly, because point of contact between the reactant molecule is maximum, and that's why actually reaction proceed actually. While in the case of heterogeneous catalysis, the reactant, catalyst and product are in different phase actually. So in the case of homogeneous catalysis or homogeneous reaction, that whatever the product is formed, it is in a mixture of reaction mixture, and all are in one phase. Means product is also in one phase. So what happens? Product isolation becomes difficult. But in the case of heterogeneous catalysis, as product is in different phase, reactants are in different phase, and catalyst is also in different phase, what happens? That product isolation becomes easy. Impurity formation becomes less. But the point of contact between the reactant molecules is little lesser. But it is economically viable because you are getting a product in pure form more easily. So the selection of most advantageous method of product isolation, purification, whatever the effluents are there, that actually should be treated before sending into the surrounding environment. So these are the most suitable operations, and the best full scale equipment, the whatever the equipment we are using, that should be of full scale actually. So these are the essence of process development. So the basic parts of process development are process design, process engineering, and scale up procedure. Process design involves determination of all items necessary to construct a plant or to run the process, including the piping, instrumentation for process control, auxiliaries, operations, and equipment. So whatever we carry out research, it should be scalable one. And once, how we can decide it is a scalable one or not? We need a chemical engineers or engineers to design a reactor so that whatever the process we are developing, it should cater the need of market. And for that reason, scale up is required. The most significant part of process development is a scale up of reactor or those equipment items of which the performance at full scale is difficult to predict sufficiently accurate. So we have to also consider the risk associated with these predictions. The base process must be selected from the subset of all process options, thus can be quite far from the global process option. Process development must be planned well to anticipate changes, and one must consider the need for increasing batch sizes of product as important objective of the scale-up efforts. So we will see, just superficially we will go through the steps in process development. Whenever somebody is given a project that you have to develop a process for some API, so what are the essential steps actually that are given over here? So first is a laboratory study. Laboratory studies means what? Whatever the project is assigned, even when I was doing, I was a research trainee in Unichem laboratories, we are working on some synthesis of API intermediates actually. Whenever the project used to come, then first we will carry out a laboratory study, whether this reaction step is feasible in our infrastructure of our lab or not. That is first criteria. And what kind of equipment will be needed, how we can carry out the reaction, which kind of reactor is needed, solvent and everything, reactant, catalyst, whether they are available or not, that everything comes into a laboratory study. So literature survey is very important aspect of laboratory studies actually. So we have to carry out literature survey. Based on the literature, actually we have to actually start the practical work on some gram level, we can say, on in some cases on mg level also. We have to start with the chemical reaction in the lab. We have to carry out the reaction. We have to check how it is going, how much time it is taking, what is the role of catalyst, how the catalyst is playing role. We have to carry out the solvent optimization study. We have to carry out the catalyst optimization study. We have to compare our research results obtained from laboratory study with other literature work. What are the purification methods we are adopting on lab level? So right from the starting of the weighing, the first we can say is a weighing, storing of the chemicals to the end product, getting end product, all things we have to minutely evaluate in laboratory study. And based on that, we design a concept. And for conceptual design, various softwares are also used actually. So based on the laboratory study, we design a concept, and after that, we focus on individual steps and we will try to develop it, optimize it, and standardize it. And once we have developed it, optimized it, then we will go for pilot plant study and mini plant study. Once it passes the pilot plant as well as mini plant studies, we have to check the environmental aspect of that. Whatever the process we are developing, is it hazardous to the employees which are working in that area, those who are handling that chemicals, is it hazardous or not? If it is hazardous, how we can replace it with greener approach or greener chemicals, that we have to check. Then process evaluation, we have to, whatever the process we are developing, we have to carry out the process profile analysis of each process. That involves capital investment, that involves operating cost, that involves regulatory norms, patent infringement or not. So process evaluation is also called as a process profile analysis, where whole process is analyzed in terms of infrastructure, in terms of operating cost, in terms of capital investment. And then once we pass that, we have to go for scale up study, because the need of market is huge and we have to cope up with that need. So we have to gradually carry out the scale up. Actually, the scale up is done gradually, as well as using some mathematical formulas. We can carry out direct scale up as well. And when you are carrying out the scale up, one of the most important aspect is purification techniques. As you are dealing with tons of product, in laboratory we are dealing with some gram of product. So purifying gram of product and purifying the tons of product is different totally. So the what kind of a purification technologies are used for carrying out the purification of that final product, that is very essential to get a spectroscopically pure product. As all of you know, the pharma industry and pharma regulations, US FDA, are having very strict norms about purity. So these are the steps in process development. Generally, we discuss these steps in process development with different case studies for around 3 to 4 hours. Next topic is need for process development. Why there is need of process development? So we will see the structure of India's pharmaceutical market. India has a national security concern arising from reliance on single foreign supplier of API, which may not always have India's best interest in the mind. India is largely dependent on China for almost all API manufactured by fermentation route, such as penicillins, cephalosporins, and microlides. In 2016, the Ministry of Commerce and Industry stated in Lok Sabha that there is a significant dependence on import in the case of 12 essential drugs. Examples: the paracetamol, metformin, ranitidine, amoxicillin, ciprofloxacin, cefixime, acetyl salicylic acid, ascorbic acid, ofloxacin, ibuprofen, metronidazole, ampicillin. There are around over 300 drugs. There is a list of national list of essential medicines, which list is around 374 drugs, and all these 374 drugs around we are taking from foreign supplier, and especially the 60 to 70% we are relying on China. So actually it is a national security concern for India that we are dependent on other country for API. We get a API and we formulate it. We are good at formulations actually, but for synthesis of API we are not that much good. Why so? We will see in upcoming slides. The key challenges faced by Indian bulk drug industry is that first is the inadequate government support. Next is the complexity in getting approvals for setting up a manufacturer plant. Next is the complex regulatory structures and price control regime. Infrastructure challenges, high cost and low availability of utilities. So these are the challenges are faced by bulk drug industry. The structure of India's pharmaceutical market in terms of disease burden in India, around 64 millions of cases of cardiovascular diseases were reported in 2015. Then 69 millions of diabetes, 2.8 millions of tuberculosis, 1 millions of malaria. And if you see other diseases, there are so many diseases are there, and there is a burden. For that, actually, for that API, for the treatment, we have to depend on foreign supplier like China, Thailand, Malaysia, and different countries. So you can see this data is about 2016 to 17 because every 10 years the data we get. So import dependency on few national list of essential medicine, you can see that around 98% of digoxin we have imported, captopril 100% we have imported. In the case of metformin, which is a diabetic drug, actually 89% we have imported. While isoniazid, which is a tuberculosis disease, around 90%, 99% we are exporting it from foreign, importing it from foreign supplier. Similarly, rifampicin, metronidazole, vancomycin, we are importing it from foreign supplier. So in 2016, India imported nearly 271.8 millions of kgs of bulk drugs and intermediates, which is valued at nearly USD of 2.8 billion. So the import of APIs have grown at current annual growth rate of 11% from USD of 800 million in 2004 to USD of 2.8 billion in 2016. And China alone contributes around 60% of all such imports by volume and 70% by value in 2016. The share of other countries in India's API import basket is small as compared to China, that is Indonesia, Singapore, US, Korea, Thailand. So over dependency on any other countries creates a significant risk for India's domestic supply of essential drugs. And also, for example, the shutdown of several Chinese API production units during 2008 Summer Olympics disrupted the supply and also increased the prices of many drugs in India. And also during COVID period, actually, the two drugs were very famous, that favipiravir and remdesivir. And you know, for the remdesivir, that injection, the people have given around 10,000 per injection, around lakhs of rupees have been spent. That we can say that black market was also there in that case. Why? Because the raw material from China actually got stopped due to COVID. Many of the another drug was favipiravir, which was tried initially for COVID, which is antiviral drug actually. That is also the process for that synthesis of that favipiravir, remdesivir was not with every company. It is what with selected company, and they are having their patent actually. So that developing a process for existing API or API intermediate is very crucial. I would like to give an example, that simple salicylic acid. Okay, we heard the salicylic acid many times actually. So you will be surprised to hear that even for salicylic acid also we are relying on China. Actually, we synthesize salicylic acid based drugs, APIs like aspirin, sulfasalazine, then choline salicylate, para-aminosalicylic acid. So we synthesize the salicylic acid based drugs in India, but actually that we can say that the raw material, the salicylic acid, generally we import. Few manufacturers are there in India who prepare salicylic acid actually in around in India, but majorly we are dependent on China. Why? Because also one factor is very important, that API imports from China, that 80% of the respondents stated they are dependent upon Chinese API because the price difference between the Chinese and Indian API is significantly lower. The Chinese APIs, they are significantly lower, 25 to 30% as compared to India. Why so? Because they are having the process chemist, they are focusing on process chemistry more, and they have built up very huge plants for synthesis of API or API intermediates. Consider if company, one pharmaceutical company is there, if it is synthesizing one API, we can say, just like we have discussed about sulfanilamide. So that company will not start synthesizing from raw material. It will take an intermediate from other company. And that other company, second company, will take an intermediate raw material from other company. So in India, that chain of the synthesis is there. Somebody is synthesizing precursor, somebody is synthesizing intermediate, and because of that, cost of the product increases. Also, we follow the traditional method of synthesis actually, because whatever the plant is developed actually, that we don't want to disturb that pharmaceutical manufacturing plant. Whatever the existing traditional methods are there, that only we are adopting. So because of that also actually, we are little bit behind China, more behind China we can say, for synthesis of API or API intermediates. And also there are different as India got a coastal region, and there are so many petroleum refineries are there actually. So many of the petroleum refineries, their byproduct is benzene, aniline, toluene. So these are actually, this raw material can be used for synthesis of API or API intermediates. So now our government is shifting their focus, and they are feeling a concern on dependency on foreign supplier. So they are actually trying to synthesize the API or API intermediate in India itself. So because of the import from China, many of our API plants in India becomes non-functional. So example is Alembic Pharma, Sarabhai Pharma, even some plants of lupine, Sandoz, that also got shut down actually. Some are partially operational, some are closed as well. You can see the bulk drugs and their manufacturers and their current status. So, in order to reduce the dependency on API imports from China, the government of India is exploring ways to boost infrastructure and reduce cost of production. In 2013, the government set up a Katoch committee headed by VM Katoch with an aim to design and formulate long-term policies and strategies that could boost the local manufacturing of API in the country. So, in February 2015, the committee submitted its report and consisting of recommendations such as providing land to manufacturers at concessional rates and other incentives or perks and easing the regulations they have tried and they are trying. So what is the scenario of R&D in synthetic chemistry? That whatever the industries are there, they are adopting a traditional methods because their plant is already set. To disturb that plant or to replace with some other, it's quite costly. So scale up, they are more focusing on scale up and they are also focusing on API or API intermediate synthesis. While the institutes, research institutes, they are focusing on libraries of synthesis. While industry focuses on one API, but we generally, the research institutes synthesizes the libraries of synthesis to check the substrate scope of reactant molecules, whether we'll get more activity with some other derivative or not. So that research generally happens in institute. Then API and natural product synthesis also is currently undergoing in institution, and also API and API intermediate synthesis on little gram level or we can say low level is happening. So to improve the traditional methods from hazardous to less or non-hazardous method, reagent, chemicals is very important challenge, and that's why we need to develop a novel methodologies so that we can compete with other competitive players from other foreign supplier. So we will just go through within 5 minutes hazards associated with chemicals, because why green chemistry is needed. So you know that DDT, that Silent Spring mentioned the harmful effect of DDT on birds. It got bioaccumulated in birds and causes eggshell thinning and dramatic population decline of birds. Also, you know about the thalidomide tragedy. That drug was used to treat a pregnant woman in 1962. Then it was withdrawn from market after several reported newborn with birth defects. Then Minimator disease, which was in Japan, it is because of methyl mercury was present in industrial wastewater, and it causes disturbance in aquatic life and as well as to humans as well. It causes disturbance. Then we know the Bhopal disaster, the dangerous gas, 45 tons of dangerous gas, methyl isocyanate got escaped from Union Carbide plant in Bhopal, India, and it also caused actually hazards to humans. Then Chernobyl disaster was nuclear accident at Chernobyl nuclear plant in Ukraine. So if you see, there are so many hazards where we have faced actually. So for that reason, there is a need of green chemistry. What is a green chemistry? It is a sustainable chemistry which says that develop a chemical product or process in such a way that it should be non-hazardous, it should have less wastage generation, moreover, the efficiency is very high. So develop a product in such a way that there should be less harmful impact. So risk associated with it, hazard, wastage, energy, cost, that should get reduced, and green chemistry is meant for that actually. Green chemistry uses the principles of renewability, reusability, atom utilization, and energy efficiency. we will see what is the green chemistry. The traditional process, the chemical process was there. The products we are forming and waste we are getting, and we have to control the pollution. But when we adopt a green process approach, where we use a raw material and energy, we modify a chemical process, and that is called as a process development. And we try to recycle the waste, and we try to use the chemicals which are not hazardous one. And sometimes we need some hazardous compound in reaction that is essential. Then we try to generate it in situ. We try to reduce the steps of synthesis so that need of chemicals, the requirement of need of chemical get reduced. One example is one pot multi-component synthesis, where we take 3 to 4 reactor at a time and try to synthesize the API or API intermediate that through one pot multi-component synthesis, so that our steps of synthesis get reduced. So green process aimed at higher income at lower pollution control cost. So there are 12 principles of green chemistry. We will just go through it. First is waste prevention. Second is the atom economy. What is it by atom economy? Atom economy means what? That whatever the reactant you are putting into a chemical reaction, the product should get all the reactant. Means minimum wastage of reactant should be there. Means A plus B giving rise to C, that C should contain 100% of A and B. If it is there, then it is called as it is a 100% atom efficient process. But generally the 100% atom economy is not achieved. It's an ideal concept, but 90 to 95% can be adopted, or can be we can develop a process accordingly to get that target. Then prevention of or minimization of hazardous products. Then designing safer chemicals, use of safer solvents, design of energy efficiency, then use of renewable feedstocks such as biomass, use of solar reactors, use of solar energy, then reduce derivatives, use of catalysis to minimize waste, to achieve the selectivity, to get the high yield product, or we can say to reduce duration of reaction, energy demands. Then whatever the catalyst, whatever the reactant we are using, they should be degradable one. They should not remain in environment for a longer period. Real-time pollution prevention is also important, and safer chemistry for accident prevention. So these are the principles of green chemistry. So now how we can improve methodologies for synthesis of API or API intermediates using some ways. So here one of the approach is substrate selection. So substrate selection, that consider if we are putting some reaction, we are synthesizing some antihypertensive like nifedipine. So when we are synthesizing nifedipine, it is synthesized maybe from 2 or 3 reactants actually. So we have to select a reactant or substrate in such a way that it should be easily available, it should be less or non-hazardous one. Then reaction conditions such as whatever the catalyst we are using or reagent using, that should be eco-friendly. That if it is a catalyst, it should be recyclable one. Use of safer solvent, as water is universal solvent, so generally water is a preferable solvent, but not all organic reactions proceed through the water, so we have to use organic solvent. So we have to check the safer solvent accordingly. The temperature, ideally our reaction conditions should be of temperature should be room temperature. The time, the short duration the reaction should proceed using within a short duration. And next one is the advanced technologies. The use of advanced technologies such as microwave reactor, flow reactor, ultrasonic reactor, solar chemistry, and mechanochemistry. We will just 2 minutes we will give to this advanced technologies. The microwave irradiations are used to carry out the reaction actually. So microwaves are high energetic waves. They causes a rapid collision and interaction between the reactant molecule, so that reaction proceeds at high rate. And generally, if you see the microwave assisted reaction, they are solvent free as well. So need of solvent is also reduced. Next one is a flow reactor. Flow reactor is what? That the reaction happens in a flow way. So there are two or three inlets. Through that inlet, the reactant are passed in slurry in some suitable solvent, and there is one mixing chamber. And that in that mixing chamber, if you need a heat, if you need some other advanced technology, you can adopt there. And in that mixing chamber, which is in a flow way, the chemical reaction happens, and then you get the product. So flow reactor is what? Where the reaction happens in a flowing way. So just like we can say that when we grind some material, we put from hopper and you get the product. So similarly, through the flow reactor, through inlet, you pass on the reactant, and reaction happens through mixing and reactor chamber, and you get the product. So flow reactor is currently the many pharma industries are adopting because it is a continuous method, and you can also adopt some other advanced technologies simultaneously with the flow reactor. The flow reactor with solar reactor, that in combination also it can be developed, and it is developed. Then ultrasonic reactor, where ultrasonic waves are used for catalyzing chemical reaction. Then solar reactor, where solar radiations are used for catalyzing chemical reaction. So solar radiations actually contains UV as well as infrared radiations. So that UV as well as infrared actually causes chemical reaction. So that is a solar reactors. And mechanochemistry approach is what? That where you can use a mechanical means ball mill, hot melt extruders, where you can use a mechanical means to assist chemical reactions. So these are various ways to improve methodologies. So example of the substrate selection here I have taken of the aldehyde or carboxylic acid. So they are easy to store and they can easy to use. They are easily available, stable carbonyl compound, and it can be used in conversion of different functionalities. They are widely used in API intermediate synthesis. So here are the examples, the conversion of aldehydes to different functionalities. You can convert aldehyde to pyranopyrazoles, 3,4-dihydropyrimidinones, 1,4-dihydropyrimidines, tetrazoles, isoxazolones. Different are there actually. Different functionalities can be synthesized using aldehydes. The drugs such as nifedipine, inastone, monastone, that also can be synthesized using aldehyde as a substrate. So, while selecting reaction conditions, chemists always try to apply the green chemistry principles, where catalysts are used, solvents are used, the safer solvents and auxiliaries, temperatures designed for energy efficiency, time for design for the energy efficiency. So we'll just go little fast. So advanced technologies, they are designed for energy efficiency. So examples are given. The Hansch dihydropyridine synthesis is synthesized using microwave reactor. Examples of flow reactors, the substituted triazoles and quinazoles. These are important intermediates for APIs. Ultrasonic reactors, the isoxazoles are synthesized. For solar reactors, actually through solar reactor chalcones are synthesized. Advantages of the advanced technologies, they accelerate the rate of reaction, the use of lower amount of energy. But limitations of the advanced technologies are they need a spatial advanced instrumental setup, skilled worker, and they may cause an issue in prolonged use or sale. So, which are the factors influencing the process choice? So, these are the factors. The cleaner, safer technologies are needed. Green approach we have to adopt. Zero emission plant. Reduction of waste. Excellent yield. Without all we have to do without compromising the yield. Our process should be economical. So, the process uses less solvent in the reaction, then it is a green. If it is a less time, it is a green. If it gives more yield, it is a green. If it is uses renewable energy, it is green. So you can see likewise if it generates a less effluent, the process is green. So now there are tools for green chemistry implementations. We have to find out the atom economy. Atom economy is a conversion efficiency of chemical process in terms of all atoms involved and desired products produced. Then E factor is an environmental factor, is another simple metric how our green reaction is. It is defined as the ratio of a mass of a waste per mass of a product. Then process mass intensity, it is a measure of manufacturing process efficiency. There is also one more tool, that is an eco scale factor calculation, where we find out the score, where how much our process is greener. So these are the various green metrics to assess our process whether it is green or little harsh one. So now we will go through some case studies. So this is the case studies which I am going to discuss for last 5 to 10 minutes is that about the work which we have done in our ICT, and also we will discuss some more case studies which are commercial one as well. So CSAR, the concentrated solar radiation assisted synthesis. So here that concentrated solar radiation as a renewable heat source for preparative scale and solvent free Bignelli reaction we have carried out. Through this Bignelli reaction and through this CSAR, actually we have synthesized two anti-cancer drugs which are inastron and monastron. And you can see this setup over here, that this setup actually we have actually carried out at the terrace of our ICT. So we use some lanes and we carried out the reaction. So the three reactants we used, that is aldehyde, beta keto ester, and some urea or thiourea, and under solvent and catalyst free conditions. So important is that we are not using solvent, we are not using catalyst, just reactant, and the solar radiations are concentrated using this Fresnel lens and solar radiation assisted reaction, and the reaction was completed within 3 minutes. Generally, if you compare the other processes, the reaction takes around 2 hours to complete, but we have actually synthesized this product within a 3 minute. So this and inastron and monastron, two anti-cancer drugs we have synthesized. Then solar energy as a renewable energy source for preparative scale as well as solvent and catalyst free for Hansch reaction. Similarly, we have taken some other reactants and we synthesized two antihypertensive drugs such as nifedipine and diludin, and the reaction time was also very less. And one more significant feature of this case study is that we have used non-toxic ammonia source. Many of the previous literature, they have used ammonium acetate or ammonia solution as a ammonia source or ammonia reagent, but we use ammonium carbonate. So once we put that ammonia carbonate, you get a effervescence of carbon dioxide. So what happens here, that reactant to product conversion becomes high, and whatever the CO2, it is released into the surrounding. Actually. So, but in the case of when we use a catalyst, reagent ammonium acetate, the side product acetic acid is there, and that acetic acid further catalyzes the reaction of final product. So immediately this final product becomes unstable and it get converted to other form. So we have achieved this, and we have published this also. So next one is that CSAR assisted synthesis of pyranopyrazole, where we have find out the eco scale factor, E factor, and also the atom efficiency, and using other reactant, using same methodology, we have synthesized pyranopyrazoles. The E factor which we have calculated, which we obtained for our work, is around 2.89, and with ethanol recycling, for recrystallization of recrystallization we need ethanol. So if we recycle that also, the E factor becomes 1.60. Ideally E factor should be 0, but it should be nearby 0. So our process is nearby 0 E factor, and literature work, if we compare, it is around 23.08. So you can see the available literature work that E factor is around 23. But when we carry out the reaction using solar radiations, actually we got E factor closer to 0. And eco scale factor, ideally it should be 100, and our work we got a eco scale factor of 98, and literature work we got a 75.5. That literature work methodology got. So it shows that our process is greener as well as environmentally benign. Then this one more important reaction is there, which is assisted by twin screw extrusion, where our HOD sir, Joshi sir, actually they have carried out this reaction in ICT Mumbai using hot melt extruder, and actually they carry out the continuous manufacturing of dihydropyrimidinones. Actually, further we have used the L-proline, L-proline, which is an amino acid which is also act as a bifunctional catalyst, as L-proline contains acidic site as well as basic site. So efficient one-pot multi-component synthesis of 1,3-thiazolidine 4,1s using L-proline as a catalyst in water, that we have carried out. And we also checked our E factor and eco scale factor and compared with literature one, and we found out that it is we can say greener one. Then we synthesize the guanidine hydrochloride, which is an organocatalyst assisted one-pot synthesis of 2-amino-4,6 disubstituted cyanopyridine derivative, which is an important intermediate for API. And we develop a sustainable greener strategy, and with catalyst recyclability. We have recycled this guanidine hydrochloride around 4 to 5 cycles. Actually. So this work is also recently published. Then we discussed about beta cyclodextrin, that use of beta cyclodextrin, which is a supramolecular catalyst for synthesis of efficient and expeditious synthesis of benzodiazepines, and under aqueous conditions using water as a solvent. So yes, so the next one is the process chemistry of API case study. So actually this topic is a little huge, so I would like that we will just discuss one case study about bromohexene hydrochloride. The lecture is designed to have an overview of API process development, including issues related to safety, environment, and economics. So we will just see the bromohexene hydrochloride. We have to identify suitable brominating agent in manufacturing of API, replacement of ozone depleting solvent in manufacture of API, and we have to use a Ranley nickel catalyst in place of traditional Bicamp reduction. So these are the bromohexene hydrochloride and ambroxazole, and their case studies here. We'll directly go through original process. So 2-nitrotoluene using N-bromosuccinamide bromination, you get 2-nitrobenzyl bromide. And then further using carbon tetrachloride and N-methyl cyclohexylamine, you get 2-nitro-N-cyclohexyl N-methylbenzene and Bicamp reduction. Through bromination, you get this bromohexene hydrobromide, which is further hydrolyzed to bromohexene hydrochloride. So we have to focus on this NBS, N-bromosuccinamide, benzoyl peroxide, which is toxic one, and carbon tetrachloride, which is the ozone depleting. So the methodology has been developed by one researcher. The reference is given at the end. So they have used 1,3-dibromo-5,5-dimethyl is a suitable versatile organic reagent alternative to NBS, N-bromosuccinamide. Then carbon tetrachloride is health hazard. So instead of that, actually, they have used other solvent. Alternative solvents were tried, and chlorobenzene was found to be the best alternative of solvent of choice, meeting all criteria. And then you can see, and instead of benzoyl peroxide, AIBN is used as a catalyst for chemical transformation of the first step. So you can see 2-nitrotoluene is converted into 2-nitrobenzyl bromide using dibromo-dimethyl using chlorobenzene as a solvent and catalyst as a AIBN. Then using chlorobenzene, you get further product, and you have use a Bicamp reduction to get a bromohexene hydrobromide, and bromohexene hydrochloride is further hydrolyzed. We get a product. So this is a modified process for a bromohexene hydrochloride. So yes, I think almost it's an 11:40. So I would like to end over here. And if anybody has any question or doubt, we can take. Otherwise, we'll end. Am I audible? मला आवाज येत नाही. आय एम नॉट एबल टू. तुमचा आवाज येतो, याच्यावर येत नाही. Yes.
Sir, am I audible?
Yes, you are audible, madam.
Yes. Sir, the question is from Anuradha Maudhu. As we all know, catalysts used are very expensive, like platinum. Can green chemistry approach help us in developing some low-cost and sustainable catalyst?
Ma'am, can you repeat question?
Sir, as we all know, catalysts used are very expensive, like platinum. Can green chemistry approach help us in developing some low cost and sustainable catalyst?
Yes, 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 yes. So yes, platinum and other also palladium is a cross-cutting catalyst actually. For that reason, we have to check we have to go through literature and we have to go for trial and error. And also we can use some advanced technologies such as microwave irradiation, concentrated solar radiations. So for platinum, I have not personally worked on this, but yes, we have to find out. That is the research and development.
Okay, sir. Sir, next question is from Dr. Dhanashri Mari. In a solar concentrated reaction, how can we control the temperature and rate of reaction? Is there any chances of overheating and degradation of product?
Yes, just showed my graphical abstract. We have monitored the reaction and we have completed that reaction within 3 minutes. If I would have kept for 4 to 5 minutes, of course that product may get degraded. So that's why we have controlled it actually using just within a 30 seconds we used to take a TLC for how much chemical transformation has been happened, and around 3 minutes we got that around above 95%, 98% chemical transformation has happened. So we immediately removed that actually, and we have cooled it and we have immediately recrystallized with ethanol and we got the product. So yes, there are chances of overheating, and your product is thermolabile, then chances is there, but it depends on the nature of the final product as well.
Okay, sir. Thank you, sir. Mhm. Any other questions from anyone? Okay, one question is from Professor Khemchand Khurana, sir. Is any protocol to select the green catalyst from the natural source?
Uh, it depends actually. So there is no as such hard and fast protocol for this. When we are working actually in a laboratory, and when we are publishing also our material, our research, so we try to find out uh, you can say catalyst based on natural origin, like biocatalysis, lipase is an enzyme, urease is an enzyme. So we try to explore the use of that uh, biomass for our chemical reaction. Even simple our lemon juice can also act as a catalyst because it contains citric acid. So there are many papers are published based on this biocatalyst. Also, enzymes such as urease, lipase. So many papers are published. So there is not that much hard and fast protocol for this. Just we have to find out the suitable catalyst and we have to check whether our reaction is going through. For that reason, we should know actually that thorough chemistry of that chemical reaction and the catalyst and catalyst sites. That how that catalyst can help in our chemical reaction.
Okay, sir, one more question is there. Sir, as the Khemchand Khurana sir is working on the modification of taking rearrangement by using catalyst from natural sources by replacing hydrogen peroxide, is any protocol or any criteria to select natural sources?
Instead of hydrogen peroxide, you are saying. Can you repeat the question again?
In taking rearrangement by using catalyst
Which
from natural
rearrangement?
sources,
Which rearrangement?
taking rearrangement
Okay. Okay. So what is that in that?
from natural sources by replacing hydrogen peroxide, is any protocol or criteria to select natural source?
So I don't know about that. I'm not worked on that reaction. So really I don't know.
Okay, sir.
Yeah.
Please share. Sir, one more question from Ankit sir. What are the common challenges faced when scaling green chemistry processes from lab to industrial production?
Sorry.
What are the common challenges faced when scaling green chemistry processes from lab to industrial production?
Okay, there are actually different challenges are right because scale up is most important thing because whatever we carry out, whatever the scale up, whatever the level we are working on in the laboratory, we worked on around gram level or we scale up it to just like in solar radiations which I have shown actually that we have done a scale up of around 10 kg using solar radiations, but converting that 10 kg into tons is very difficult task. It requires expertise. It requires engineers to design a reactor. So scale up is most important aspect where you have to uh, scaling up that laboratory to tons of level actually scale up. So scale up is most difficult, one of the challenge actually we face, and also infrastructure that on lab level we use small vessels. For the scale up purpose, we need a high reactor size. We are also introducing chemicals, in removing the reaction mixture for TLC monitoring as well. Actually, so handling that large amount of material is also itself a challenge, and it needs expertise. Actually,
Okay, thank you, sir. Thank you all the attendees for your participation.
okay, yes,
Wait, sir. Certificate. It was indeed a great session, sir. On behalf of Gokhale Education Society, Sir Dr. MS Gosavi College of Pharmaceutical Education and Research, Nasik, I would humbly request you to accept the certificate as a token of appreciation and would extend my sincere gratitude to you for taking time out of your busy schedule to join us for the webinar. Thank you, sir.
thank you, each and everyone for attending the class, and thank you. The authorities of MS Gosavi College and Principal, Vice Principal Shweta Madam for giving me opportunity to share some research aspect of our group to all of you. I really thank each and everyone, and I would like to also thank the students who are the main receiver of the knowledge. So yes, thank you each and everyone.
Thank you, sir.
Session.